6.6, work energy. So typically when we're thinking about work energy for rigid bodies now, the gravitational potential energy, that doesn't change, right? It's wherever the center of mass is. And like work done against springs, that doesn't change. The work done against other types of forces, that's all the same. But the only thing that does change now is the kinetic energy. So for the kinetic energy, we have this T, and now before we were talking about how that's 1/2 mv squared. This is for a point mass, and now if our rigid body was just translating, we would just have this, but make sure you want to take about the center of mass, so V bar. But if it's rotating as well, we're also going to have this component. And this takes into account the fact that on a rigid body like this, right, even if it's moving in some way like this, I'm also rotating. Now, this small mass here is going to have energy not just from the translation of the whole thing, but it's going to have an additional velocity at this point. So that's all taken care of in this term. All right. In terms of other special cases, if you have fixed axis rotation, then you can have T equals 1/2 I about that fixed axis times omega squared. If you have translation, you can say just T equals 1/2 mv squared. So where the velocity is just the velocity of the whole thing, because by definition, if you're translating, the velocity is the same everywhere. And now for an instant center, what we can say is we can say that T equals 1/2 I about that instant center omega squared. So this is kind of cool. It's just like you can, at some instant, just like we talked about with velocity before, if you know where the instant center is and you know what I about that instant center is, or you can find it using the parallel axis theorem, then you know that the energy at that instant is going to be 1/2 I of about that instant center times omega squared. All right, so these are the equations that we're going to use to do the problems.